यस सर।
ये लास्ट टाइम हम डिस्कस कर रहे थे थ्योरीज, यस सर।
हाँ
थ्योरीज कंप्लीट हो गया था, कुछ रह गया था इसमें?
थ्योरीज में वो सीएफटी का एक क्वेश्चंस पूछे थे आपने, बीवीटी और सीएफटी का डिफरेंस क्या है।
यस सर, डिस्कस करते हैं, यस आगे इसमें चलते हैं। इज व्हाट द डिफरेंस बिटवीन बीवीटी एंड एलएफटी या अदर वन, एमओटी, ये सीएफटी?
सर वो एलएफटी वाला पार्ट मैंने अभी तक नहीं पढ़ा है, वो मैं आज ही पढ़ लूंगा। वो एलएफटी का पार्ट और जो लास्ट में जो रिएक्शन मैकेनिज्म वाला पार्ट है, वो पार्ट मैंने पढ़ा नहीं है ठीक से, वो मैं आज ही कंप्लीट कर लूंगा। और ये जेटीडी, ये जो
यस
सीएफटी है,
यस।
सीएफटी की जेटीडी मैंने पढ़ लिया है, जेटीडी हो गया है। तो आज ही मैं वो ऑर्गेल वाला पार्ट, ऑर्गेल डायग्राम और ये एलएफटी एंड रिएक्शन मैकेनिज्म कंप्लीट कर लूंगा।
ये जॉन टेलर डिस्ट्रेशन एक्सप्लेन कीजिए, यस। व्हाट इज जेटीडी?
हाँ
व्हाट द मेन एप्लीकेशन ऑफ जेटीडी इन कोऑर्डिनेशन?
ओके सर, JTD is a type of distortion is seen in the coordination complex. It causes because some instability or some unstable electronic configuration takes place in the coordination complex, and it affects the bonding or the bond length of the coordination complex. So JTD means John Taylor distortion. There is three type of distortion we can see in coordination chemistry. One is Z out, one is Z in, and one is triaxial distortion. So in case of Z out, the structure of complex will be looking like this, where the axial bond length are getting bigger, and in this case axial interaction occurs more. So the splitting is also has some changes in case of Z out interaction. We have seen in CFT the d orbital splits itself to EG and T2G. Now in case of JTD, it further splits and show this type of splitting. This is XY, and this is dz square, this dx square minus y square. This is the Z out splitting of John Taylor distortion. In this case, there is 4 short bond and 2 long bond, and here it is said that Z out distortion is tetragonally elongated. Now, in case of Z in, what we have seen that the equatorial bond length are getting bigger than the axial bond length. So it is basically tetragonally compressed. Tetragonally compressed distortion. And here also the splitting of d orbital changes. So from the splitting from CFT, we can show how the splitting of Z-in interaction takes place. So as the interaction between metal and ligand in the equatorial position decreases, the energy of the this is the splitting for Z-in distortion in complex. And what is triaxial interaction? Triaxial interaction is XYZ distortion. In this case, an example can be used to show how triaxial interaction occurs. In this case, the bond lengths are not equal and distorted itself and makes this like compound. So these are the main concept of John-Taylor distortion we have seen. These are the splitting in case of John-Taylor distortion, and this is another type of John-Taylor distortion we can see. So now, which type of compound shows John-Taylor distortion? We will talk about that. So in case of the coordination complex having unpaired electron, or basically unsymmetrical EG or T2G, shows John-Taylor distortion. The compound having unsymmetrical T2G orbital or EG orbital shows John-Taylor distortion. How? Because in this case, coordination complex always try to remove its electronically degeneracy and lowers its symmetry. This can go to here, this can go to here. And also in EG, this degeneracy is created, but JTD or John-Taylor distortion always tries to lower the symmetry and remove the electronical degeneracy. So we should see an example where John-Taylor distortion occurs. Now we are taking a complex which will show John-Taylor distortion. In this case, we are taking hexa-aqua manganese, and in this case the d electron conformation will be d4, and the splitting of this compound will be P2G EG. So in this case, what we have discussed that we should get the unsymmetrical T2G orbital or EG orbital. In this case, we can see unsymmetry or asymmetry in T2G. So this compound shows John-Taylor distortion. So what will be the benefit of John-Taylor distortion, or what will be the limitation for John-Taylor distortion? It is known that John-Taylor distortion increases the thermodynamic stability of a compound, and also John-Taylor distortion increases the kinetic reactivity of a compound. But there are two types of John-Taylor distortion. One is called dynamic John-Taylor distortion and one is called static John-Taylor distortion. Dynamic and static. So what is dynamic John-Taylor distortion? In dynamic John-Taylor distortion, ZTD is present, but we cannot trace that experimentally. We cannot observe experimentally. And the static ZTD is present and we can observe experimentally. In dynamic ZTD, the distortion is so fast that we cannot observe this type of distortion. This is why it is called as dynamic distortion. An example will be TL2K CuNO2 whole 6. This is an example for dynamic John-Taylor distortion. And we can make dynamic John-Taylor distortion to static John-Taylor distortion by lowering the temperature. If we lower the temperature of a compound having dynamic ZTD, after some time at a certain temperature, the dynamic John-Taylor distortion showing compound will behave as static John-Taylor distortion showing compound. So this is the brief and analytical idea of John-Taylor distortion in coordination chemistry.
Yes. Is what the main purpose of ZTD in coordination?
So the main purpose of the effect of ZTD will be first the effect on bond length. In case of distortion, we can see bond length is getting bigger or getting much little. So effect of bond length is quite clear in case of John-Taylor distortion, and also John-Taylor distortion helps a compound to gain or attain thermodynamic stability. John-Taylor distortion, if a compound having John-Taylor distortion, then the compound will show more stability than others. And also John-Taylor distortion increases the kinetic reactivity of a compound. So this will be the benefits of John-Taylor distortion according to the complex theory.
Yes. Yes, what the difference between tetrahedral, octahedral, and square complex in coordination? Why tetrahedral is always high spin? Octahedral is high spin, low spin. Why square planar is always low spin? Explain one by one.
So now we will be seeing the inner phenomenon of a tetrahedral complex and square planar complex. So in case of square planar complex, we have seen that hybridization of this type of complex is sp3, and in case of square planar complex, the hybridization is dsp2. And we also see that the tetrahedral complex are more high spin complex. But in case of square planar complex, it is usually more low spin complex. Why? So now we will be seeing that how a tetrahedral complex is formed according to the hybridization theory. By this. So in case of tetrahedral complex, it is always mode of a outer orbital complex, OOC, outer orbital complex. In this case, the d orbital is quite full, so the inner d orbital does not participate in the hybridization. So the ligand donates its electron in these orbitals. This is 3d, this is 4s, and this is 4p. So ligand donates its electron to this outer 4p and 4s orbital. This is why the hybridization will look like sp3 hybridization. So in only high spin complex, or the complex which shows more spin electron multiplicity, then the participation of d orbital will be less in the hybridization. If there is no vacant orbital in inner d orbital, then ligand will not donate its electron to the d orbital. So this is why tetrahedral complex are high spin, and in the other hand, when we see the square planar complex, we always see it is kinda inner orbital complex. So why it is inner orbital complex? Because d is participating in the hybridization here. So in case of square planar complex, most of the cases strong field ligand used, and these d electron are quite paired. So when the d electron is paired and one vacant d orbital present, then in case of coordination number 4 complex, ligand will donate its electron to this vacant orbital and forms a complex, tetrahedral complex, or a complex which shows dsp2 hybridization, then we can see 1d, 1s and 2p. So 1d, 1s and 2p. So this is why dsp2 hybridization shows square planar shape, and most of the cases low spin complex are square planar complex.
Yes, good. What is electrochemical series in coordination? What are the main application of electrochemical series?
Sir, electrochemical is a spectrochemical.
Oh, spectrochemical, sorry. इलेक्ट्रो चलता
Is
रहता
a
है ना माइंड में,
spectrochemical
किसी का
series.
टॉपिक इलेक्ट्रो होता है, किसी का कुछ होता है, तो माइंड में वही चलता रहता
So, spectrochemical series contains a series of groups where it shows the strength of the ligand. So, firstly, we will see what is the actual series in this case which shows the strength of ligand. So these are the ligands which are lined upon the spectrochemical data. So this is the spectrochemical series, and from spectrochemical series we can predict the strength of ligand. And by this we can predict if a ligand is strong field ligand or weak field ligand. So when a weak field ligand or strong field ligand attached to a coordination complex, by the data of spectrochemical series, we can predict the complex will be low spin or high spin. And according to low spin and high spin, we can predict the true nature of a coordination complex and how it will act and react with other compounds. It can be also predicted by the strength of the ligand, which is provided by the spectrochemical series. So this is the benefit or application of spectrochemical series in coordination theory.
Yes, good. What is sigma bonding in tetrahedral complex? What is the MO of tetrahedral complex?
Okay.
Square planar, octahedral. Can you explain one by one? MO diagram.
सर एमओ डायग्राम अभी याद नहीं है उसका, मैं कर लूंगा.
ओके, कोई प्रॉब्लम नहीं.
आज ही कर लूंगा, आप कल पूछिएगा, मैं कल आपको सब बता दूंगा.
Yes, yes, कोई नहीं. Yeah, next move on. Next topic is color and electronic spectra. Yes. So can we explain in transition element and lanthanide actinide which type of colored and electronic spectra show of these type of elements in coordination?
Sir, can you see me?
Yes, yes, I see.
आपका आवाज थोड़ा
Yes.
Cut.
Color and electronic spectra. Next topic is color and electronic spectra. So
केलं हाँ
triethylene,
color.
lanthanide, actinide. So these type of elements show in color and electronic spectra. Explain.
Yes, sir. So in case of color theory and electronic spectra, we will see the configuration of the d orbital or the f orbital according to the element. So based on the color theory, the color can be predicted by the theory of CFT and DD transition. But in case of electronic spectra, we will use Orgel diagram to see how many transitions can be possible. And also the transition, if a transition is possible or not, is based on selection rule. There is two rules for transition. One is selection rule, in which the del S has to be 0, and Laporte for selection rule, in which it says that del N should be 0 or plus minus 1. So if an electron follows the selection rule and Laporte selection rule, then it will show the transition in the complex, and then color arises. So in case of the transition and selection, we will use the Mulliken scale parameters according to the configuration D2, D1, D3. So now I will write the chart where we can see how many transitions can occur in an element according to their L value. So in case of S, for OH, octahedral and tetrahedral, there will be two term symbol. So for S, it will be one A1G, and for the tetrahedral, it will be A1. And for P, this will be T1G, and this will be for tetrahedral, it will be T1. And in case of D, it will be T2G and EG. And in case of T1 and case of tetrahedral, it will be T2 plus E. And in case of F, it is T1G plus T2G plus A2G. and in case of tetrahedral, it will be T1 plus T2 plus A2. So these are the term in case of various L value from which we can predict the orgel diagram or the electron transition which occurs in a compound, complex compound. So firstly, I will show an example in the orgel diagram and show you a transition, how a transition takes place. So firstly, if we take D1 orbital or D1 configuration, then the term symbol will be the L value will be +2, the S will be +½ into 1/2. So 2s plus 1 will be 2 into half plus 1 equals to 2, and for L value 2, the term will be D. So the term symbol will be 2D. So for 2D configuration, what will be the orgel diagram? Then the diagram will be like this. In this case, one state will be T2G and one state will be EG. And in this case, one transition will be possible here. So this is how a orgel diagram shows us how a transition occurs in a coordination complex, and we have discussed about the D1 configuration here, and we can see one transition is possible between T2G and EG in this case. In this case, we have taken octahedral complex, but if we take tetrahedral complex, then the value will be reverse. Then the graph will be like 2D, two states here. The lower energy will be E and the higher energy will be T2. So this will be the case of tetrahedral complex, and this will be the case for octahedral complex.
Yes, good. Next is what the difference between transitions forbidden and allowed transitions. What the difference? And Lepoto forbidden, Lepoto allowed. What the difference?
Okay. So in the transition selection rule, we have seen that for transition, according to selection rule, the change in electron multiplicity, spin electron multiplicity will be or should be 0. If this rule is violated, then transition will be forbidden. According to selection rule. But in case of Laporte rule, the rule for transition according to Laporte is del L should be 0 or plus minus 1. So if this rule maintains, then the transition will be called as Laporte selection, and if the transition is not maintained by this rule, then it will be called as Laporte forbidden rule, Laporte forbidden transition. First is Laporte allowed transition, and another is Laporte forbidden transition.
Yes, what is the difference between orbital diagram and Taylor-Sugano diagram?
So in case of orbital diagram, we will see the electron transition according to the d electron configuration. But in Tanabe-Sugano diagram, we will see in the deeper aspect where the energy states and term symbol are confined in it, and it will be a more complex diagram than an orbital diagram.
Yes, what is the drawback and limitation of orbital and Taylor-Sugano diagram?
So in case of orbital diagram, we cannot predict the actual transition in all cases, and obviously there are some errors we can see, and we cannot explain some phenomenon according to the Tanabe-Sugano diagram and orbital diagram. Some transitions are still possible whether the selection rule or Laporte selection rule has been violated. So these are the these are the limitations of Forgill and Tanabe-Sugano diagrams in our coordination theory.
Yes, what is the difference between DD transition and short transfer spectra?
So in case of DT transition, we can see according to CFT that what happens in DT transition is the electron present in the T2G goes to the EG orbital, and when it comes back to the T2G, it will release some energy in which the energy releases the wavelength absorbed by the molecule complementary color or complementary wavelength